Welcome to This Explainer. Today, we're diving into what is basically a historical detective story. We're going to look at how a massive, honestly mind-boggling failure in classical physics led straight to the discovery of the bizarre quantized nature of our universe. So let's jump right in. We're traveling back to the late 19th century, a time when physicists really thought they had almost everything figured out. They had thermodynamics perfectly mapped, they had Maxwell's equations for light, and they figured the rest of physics was just filling in a few minor details. But as we're about to see, they were completely wrong, and fixing that glaring mistake birthed the entire quantum revolution. To kick things off, just think about this totally absurd idea. We all know that if you turn on an electric stove, it heats up and glows red, right? And if you get something even hotter, like a welding torch or a star, it glows blue or white. But here is the crazy part. Late 19th century classical physics literally predicted that heating up an everyday object, like that stove or even your morning toaster, would cause it to blast out an infinite amount of fatal gamma radiation. Obviously, making breakfast doesn't nuke you with gamma rays, so classical physics was predicting an absolute impossibility. So to figure out how heat actually translates to light and, solve this toaster problem, late 19th century scientists started studying what we call black bodies. Now, a black body is just an idealized object. It completely and perfectly absorbs any light energy that hits it and then perfectly re-radiates that exact same energy back out as light. By studying these black bodies inside closed cavities in the lab, physicists could measure the exact pattern of radiation they gave off at different temperatures, completely free from any outside noise. They were basically hunting for the mathematical law that explained the relationship between temperature and the color of the emitted light. And when we look at the actual hard data from those experiments, two really clear things happen as objects get hotter. First, the total amount of radiation shoots up. The peak gets much higher. Second, the peak of that emitted light physically shifts over to higher frequencies. It moves from the invisible infrared right into the visible red, and eventually peaks smack in the middle of the visible spectrum for an object sitting at 6,000 Kelvin, which, not coincidentally, is exactly the surface temperature of our sun. That's exactly why the sun looks yellowish-white to us. The data here was completely clear, smooth, and predictable. But all right, here is where the absolute crisis hits. Notice that dotted line just shooting off the chart? Two brilliant scientists, Lord Rayleigh and Sir James Jeans, used the standard, tried-and-true rules of classical thermodynamics and electromagnetism to predict this curve. And their classical theory? Well, it worked okay for the long wavelengths, the infrared stuff, but the second you moved over to shorter wavelengths like ultraviolet, the classical Rayleigh-Jeans theory completely fell apart. It predicted that the radiation intensity wouldn't peak and gracefully drop back down. It would literally just skyrocket to infinity. This was a massive, glaringly obvious flaw, and it got famously dubbed the ultraviolet catastrophe. They desperately needed a whole new rulebook. Section 1. Planck's Act of Desperation. Enter our reluctant hero, German physicist Max Planck. In December of 1900, he actually managed to find a mathematical fix for this ultraviolet catastrophe. But look at this quote from Planck himself, looking back on his discovery years later. He says, "What I did can be described as simply an act of desperation. It was purely a formal assumption, and I really did not give it much thought." I love that. It really humanizes the science, doesn't it? Planck was a super traditional physicist. He absolutely hated the idea of breaking with the beautiful, continuous 19th century statistical mechanics from guys like Maxwell and Boltzmann. But he did it anyway, simply because he was desperate to find a math formula that actually matched the physical data his colleagues were measuring in the lab. So what was this radical assumption he had to make? Well, to stop that curve from just shooting off into infinity, Planck proposed that the energy of the molecular oscillators inside the black body isn't a smooth, continuous flow at all. Instead, it comes in discrete, fixed amounts or bundles. He called these bundles quanta. Think of it kind of like a staircase instead of a ramp. You can stand on step 1 or you can stand on step 2, but there is absolutely no way to stand on step 1.5. Energy, he figured, was perfectly chunky. And that brings us to one of the most famous equations in all of physics, E equals hf. He proposed that the energy of any vibration has to be a whole number multiple of its frequency, that's the f, times a very specific constant, that's the h. This single, elegant little equation completely threw out the classical equipartition theorem that had caused the ultraviolet catastrophe in the first place. See, high-frequency light, like ultraviolet or X-rays, requires a massive chunk of energy to be emitted all at once. And because everyday objects just don't have enough thermal energy lying around to spit out those massive chunks, the curve naturally drops back down to zero. Boom. Catastrophe averted. Now you might be sitting there wondering, okay, if energy is completely choppy and stair-stepped like this, why does the entire world around us feel so perfectly smooth and continuous? Well, take a look at this number. That specific multiplier, h, is Planck's constant. It is 6.63 times 10 to the negative 34th power joules seconds. That is a 0, a decimal point, 33 more zeros, and then a 6. Because it is so ridiculously, vanishingly small, we simply don't notice this stair-step quantization in our big, everyday lives. I mean, a baseball thrown at 50 miles an hour is technically quantized, but the steps are so infinitely tiny, it looks completely smooth to our eyes. Section 2. Light as billiard balls. Okay, so this whole idea pretty quickly evolved from what Planck assumed was just a neat mathematical trick into actual physical reality. This shift was sparked by Albert Einstein in 1905, who boldly threw out the idea that it wasn't just the matter emitting the light that was quantized, but that light itself actually travels through space as localized energy quanta. Today, obviously, we call these light quanta photons. But get this, for almost 2 decades, the scientific community was super skeptical of Einstein's photons. They thought light was a wave, end of story. But that entirely changed in the early 1920s thanks to Arthur Compton's X-ray scattering experiments. Compton realized that high-energy light interacts with electrons exactly like billiard balls colliding on a pool table. The incoming light smacks the electron recoils one way, and the scattered light bounces off the other way. Compton proved this by shooting high-energy X-rays directly at electrons. By treating the light as discrete particles, photons, with their own specific energy and momentum, he had to carefully balance the relativistic energy before and after the collision. And he observed that the wavelength of the light actually shifted. It got noticeably longer after the collision because it literally handed over some of its energy to the electron. Most importantly, the exact amount of that shift depended entirely on the angle of the scatter, which is exactly what particle physics would predict. This effectively nailed it and validated Einstein's photon hypothesis once and for all. And the math behind this gave us this beautiful little expression that sets the scale for that shift. H divided by mc. That's Planck's constant, divided by the mass of the electron times the speed of light. This result brilliantly encapsulated wave-particle duality. Think about it. Compton produced light waves. He measured the shift in their wavelength, but he could only actually make sense of the math by treating the light as individual colliding particles. Light is somehow wonderfully both. Section 3. Understanding quantized energy. So why exactly does energy behave in this choppy, discrete way at the atomic level? And what does it actually mean for the physical matter we interact with every single day? Well, it really all comes down to confinement. Let's compare these two states. When a particle is unbound and just freely moving through space, its energy spectrum is continuous. It can be whatever it wants. But when a particle is in a bound state, like an electron trapped by the pull of an atomic nucleus, it's essentially stuck in a quantum box. It's just like a guitar string that's pinned down by the neck and the bridge, so it only vibrates at specific harmonic frequencies. The confined particle forms standing waves, and self-interference basically cancels out all the intermediate states. That means the particle can literally only exist at specific, discrete, quantized energy levels. Now, this brings up a massive question. If atoms have these discrete energy lines, why did those solid black-body stoves we started talking about glow with a smooth, continuous curve of light? It's all about how the atoms cluster together. In a gas, the atoms are mostly isolated, floating around on their own, so they emit distinctly quantized, barcode-like energy lines. But in a solid, like our stove or an old light bulb filament, you have something like 10 to the 23rd power tightly clustered atoms strongly interacting with each other. Yes, there are still discrete energy levels, but billions of them overlap so incredibly closely that the spacing between them essentially just vanishes. The levels blur together into what is practically a continuous energy band. So it's quantized deep, deep down, but practically continuous up here on the macro scale. And that brings us to the end of our explainer. But I want to leave you with this final, really provocative thought. Just look around you. The world seems so smooth, right? Like a sliding dial, a pure analog continuum. But as we've learned from Planck, Einstein, and Compton, if the foundational physics of light and matter actually operate in discrete, countable chunks rather than smooth transitions, well, then our reality is much more digital than our continuous analog senses suggest. So are we living in a smoothly flowing universe, or is absolutely everything around us just rendering step by step at the Planck scale? Thanks for joining me on this deep dive. Keep questioning the physical world around you.